Imagine a nuclear reactor core. It's one of the most violent environments on Earth, where subatomic particles scream through solid steel like cannonballs through a glass house. Usually, this radiation makes metal brittle, leading to microscopic cracks that can cause catastrophic failure. But engineers at Virginia Tech and Johns Hopkins have just engineered a material that thrives in this chaos. It's called a multiple principal element alloy, or MPEA. Instead of one base metal with tiny additives, it's a perfectly balanced cocktail of 5 or more elements that changes everything we know about metallurgy.
For thousands of years, we've made alloys by taking one main metal, like iron, and adding a pinch of something else. Think of it like a bowl of milk with a few sprinkles on top. But MPEAs throw that recipe book away. They use 5 or more elements in nearly equal parts. It's not a base with additives. It's a high-stakes chemical collaboration where every player is a lead actor. This creates what scientists call high entropy. Because there are so many different types of atoms packed together, the lattice becomes incredibly complex and surprisingly stable. In a standard metal, the atoms are like a perfectly stacked crate of oranges. If you hit one, the displacement travels easily through the whole row, causing a clean break. But in an MPEA, the different sizes of the atoms create a bumpy atomic landscape. It's like trying to roll a marble across a floor covered in different-sized rocks. The energy just gets lost. This atomic roughness is the secret weapon. It prevents cracks from spreading, making the material nearly immune to the brittle fracture that kills most metals in extreme cold or radiation. This isn't just a lab curiosity. The Virginia Tech team is targeting the most demanding machines ever built. We're talking about the inner linings of fusion reactors and deep space propulsion systems. In these environments, traditional steel would swell and crumble, but the MPEA lattice acts like a shock absorber at the atomic level, soaking up energy that would destroy anything else. The result is a material that is both incredibly strong and remarkably ductile. It can bend without breaking, even when the temperature drops to near absolute zero or climbs to the melting point of lead. But there's a catch. This material is so tough and its chemistry so complex that it shouldn't actually work according to traditional physics. It defies the standard rules of thermodynamics. The real genius isn't just in the mix of metals, but in how those metals react when things get violent. Because the most amazing part of this story isn't how the metal survives radiation, it's how the radiation actually makes the metal better. To understand that, we have to look at the physics of the displacement cascade. In a normal metal, neutron bombardment is a death sentence. Think of it like a bowling ball hitting a set of pins at 10,000 miles per hour. The structure just disintegrates. This creates vacancies, empty spots where atoms used to be, and interstitials, atoms jammed where they don't belong. Eventually, these defects clump together into bubbles, and the metal swells like a sponge. But in the MPEA developed by Johns Hopkins and Virginia Tech, something impossible happens. Instead of falling apart, the material uses that energy to stabilize itself. This is due to a phenomenon called stalling. In a standard alloy, a displaced atom can travel a long distance before it stops, creating a massive trail of damage called a displacement cascade. But remember those 5 different elements? Because every atom is a different size and has a different magnetic charge, they create a high-friction environment for moving particles. The displaced atom hits a speed bump almost immediately. It can't travel far, so the damage is localized and tiny. It's like a car crash where the crumple zone is only 1 atom thick. And here is the genius part. The heat generated by the neutron strike actually helps the atoms find their way back into the lattice. The material is essentially self-annealing. Usually, heat makes defects move and group together into large cracks. But in MPEAs, the chemical complexity makes it harder for defects to find each other. They stay isolated and harmless. It's a complete reversal of nuclear engineering. Instead of fearing radiation, we can now build machines that use that radiation to maintain their own structural integrity. To prove this, researchers used massive particle accelerators to simulate years of nuclear wear and tear in just a few days. The results were staggering. While traditional alloys showed massive voids, literally holes in the metal, the MPEA samples looked almost identical to how they started. The lattice had survived a subatomic hurricane. This stability comes from the lattice distortion effect. Because the atoms are slightly uncomfortable in their positions, they are always ready to shift and absorb energy without breaking. But this incredible strength creates a massive problem for the people who actually have to build things with it. How do you shape a metal that refuses to be broken? Traditional tools like diamond-ticked saws and carbide drills simply aren't enough. The material is physically too tough for conventional manufacturing. The solution required a leap into the world of high-power lasers and 3D printing. We had to stop cutting the metal and start growing it.
If you can't cut a material, you have to build it atom by atom. This is where laser powder bed fusion comes in, the most advanced form of 3D printing on the planet. The process starts with a fine dust of the 5 elements. A high-power laser then traces a pattern, melting the powder instantly into a solid layer of MPEA. By doing this, engineers can create complex internal geometries that would be impossible to machine, like cooling channels that curve through the heart of a solid block of metal.
But printing MPEAs isn't as simple as hitting print. Because the 5 elements have different melting points, the laser has to be tuned with extreme precision. If the laser is too hot, one metal might evaporate before the others even melt. If it's too cool, you get lack of fusion, leaving tiny weak spots in the part. The Virginia Tech team mastered this thermal dance, using ultra-fast sensors to monitor the melt pool thousands of times per second to ensure a perfect mix.
The result of this 3D printing process is a microstructure that is actually superior to cast or forged metal. The rapid cooling locks the atoms into their high-entropy state. This means we can now create parts for the next generation of nuclear reactors that are smaller, safer, and can run for decades without needing repairs. But the implications go far beyond Earth. Because MPEAs are so resistant to radiation and extreme cold, they are the perfect material for building the first permanent bases on the Moon and Mars.
We are entering a new era of metallurgy. For centuries, we were limited by the properties of single elements. Now, we are learning to play the whole orchestra at once. This isn't just a new metal, it's a new way of thinking about materials. We're no longer trying to avoid chaos, we're using it to our advantage. From the heart of a nuclear reactor to the vacuum of deep space, these high-entropy alloys are the silent scaffolding of our future. Next time you hear about a breakthrough in clean energy or space travel, remember the invisible lattice of 5 metals that made it possible. The engineering behind this is absolutely brilliant, turning the most destructive forces in nature into the very thing that keeps our technology alive. The world of material science just got a lot more interesting, and we're only just beginning to see what this cocktail can do.